Okay, I think we got a plan. It's all in Bob's hands now because the next video doesn't go ahead if we don't have any of these parts. Bob from the machine shop, I think take it away. It's all in your hands.
Where do I start? I can't get this wrong. This is the engine mount from Alex's crashed Bugatti Chiron. Matt was tasked with the job to repair this whole car, but everything came to a halt when he realised the engine mount was snapped.
Oh.
Matt has trusted us to fix this part. With a $6 million car on the line, I have to get this right. And this is how we're going to fix it.
Is this the most expensive thing you've had on this table?
Yeah, by a lot. Mark McCann's gearbox to repair is 300 grand, just to repair it. So I can't imagine what a part is to buy. What is this like?
Silly money.
It's not a full gearbox. It's not, what, I'd imagine 100 grand, there's 100 grand on the table. When Matt was over in America, when they got this part out, obviously it was snapped. They needed to 3D scan it to see if they could replicate it from billet. And to do that, they needed to weld it back together. So they found a Mexican bob to put a few tack welds on it. Like this. Now, you see millimeter gap here? That'll be the same over here. So the whole width of it is going to be probably 2-3 millimeters wider than it should be at the moment. So I need to get rid of that. So if we take Mexican bob's welds out, that means that these cracks here will reduce in size, and hopefully all these lines here will mesh up together without any gaps in the middle. Then I'll put a tack on it, then I can get it on the mill and I can start measuring everything. Once I've got it measured, I can break all the tacks again, start cleaning down the center, get all this dirt out of here, and once it's clean, I can put it all back together, tack weld it, measure it again on the mill, make sure everything is perfect to those original measurements. Then I can do the final weld on it. First thing we need to do is get Mexican Bob's welds off. So see the difference in the material here. So say it's a kind of a dull texture, and then across here it looks all like it's been hammered. So I think after the crash, because the boys kept driving it, it was sat here and cracked all the way across. It kept doing that as it was driving, like vibrating and hammering that area. So you've got that texture. Interesting. We have to be careful not to grind back too much of the rough material. We will use this to help locate the part perfectly. We will focus on the welds and the hammered parts, and that will give us our close fit. What I'm trying to do now is get this part fitting just perfectly. I'm being very careful not to take a lot of material away from certain areas, so I'm just bringing the surface down a little bit with a wire brush, just so it matches up. And then there's 1 or 2 areas where it's rocking like a seesaw. Now, what that's telling me is when it's snapped, it's pulled or bent one area within the casting. So they're both outsides are absolutely perfect, but the inside a little bit high. So I'm just bringing that back until this point, and this point, and this point all match. This is the only part of it that's given a little bit of trouble. So I'll just trim that away. All the rest of the points will fit, and then we should be fine. So there's about 300 millimeters of contact face across all of this. I've chosen some points on this not to fettle or touch with any of the power tools, just so they go back in the right place all the time. Now, that rock that we were talking about earlier has gone out. It's solid. It's mounted there 100%. I know it's in the right place because those 4 points are in the exact right place they should be. So I'm going to keep those 4 points untouched, and then I'm going to weld prep the area, which basically means just chamfer everything so I can get a weld deep down into the material and have a fully penetrating weld all the way through the aluminium, so it'll be stronger than before. This is the make or break moment, the bit that we've been trying to figure out for a while. We know the type of aluminium that this is cast from. We know that engineers think it's weldable, but whether it's actually weldable in real life or not,
we'll find out. On the next episode.
On the next episode. First time, every time. It's weldable. This is going to be mint.
So that means you can continue and
Yeah.
this will be
Yeah,
fixable.
that's just welded like so nice. So there's a little bit of magnesium in it, and you can see it floating to the top when I'm welding, and just sort of bubbles to the surface of the weld, and it's kind of giving a little bit of emissions around the side of it, so some dirt. But it looks and feels really good. I'm happy. I'm happy. It's weldable.
Hey!
Weldable, it's metal.
That is such a relief. Everything was hanging on that. Brilliant. Cool. I need to take that out again. I just put a weld where I didn't need it. What a relief. Now let's get it over to the mill so we can measure it. So inside of this is a circle, obviously. I need to find the center of the circle and measure out from that point to these points and see if they're equal. If they're like a millimeter out from each other, we're going to guess that there's something wrong. If one of them is 15 millimeters out, we know that it's been made asymmetrical. Right, okay, isn't it something interesting now? We were expecting these to be symmetrical, but I've just noticed when I put it down the table, this side is not a mirror of this side. Across here, compared to the shape of the casting here.
Oh.
So it's been formed up this way, and there's a bigger distance between, say, like that hole and the mill bed than there is on this side. I can't get this wrong. With all that in mind, we have to make sure we bolt this to the mill bed absolutely perfectly. We don't want to take any chance of mismeasuring something here. This is vital.
Bugatti.
Bugatti. Is it really French?
Bugatti.
Oh, it's a big Citroen. Now I have this all square and accurate. We can use this thing here. It's called an edge finder. It just makes a little noise when it comes in contact with metal, and it gives me an extremely accurate position of where the material is. The first thing I do with this is find out the exact center of this hole in the middle.
This is cool, man.
This is very cool.
This is cool.
Very cool. I just think it's like such a wild contrast from where I grew up to the stuff I was doing, what I'm actually trained to do, and what I do now. All the way from just messing around with stuff in my dad's shed when I was a kid. My dad's a carpenter and plumber, in general, kind of turn his hand to anything. You know, it was always in my house. If somebody else can do it, you can do it. That's the way we were taught. It's still wild.
It's a wild opportunity.
Wild. Okay, so what we're looking for is the distance from the edge of that to the furthest outreach of that, I'd say. Or if it's spot on, we know we're spot on. So if it's the same measurement on both sides, we're happy. We're really happy. That's the best thing. If it's 20 mil out, then we don't really have any way of measuring it. It means it's asymmetric. But if it's 2 millimeters out, then it's concerning. So the ideal thing to do would be to measure the center of that hole, but there's no way we can do that. It's on an angle compared to my mill. So we'll go to the nearest date, and we're just trying to get a feel for, or a good understanding of what shape it is. That's perfect. It turns out there's 0.6 of a millimeter in the difference between the two sides. Spread across the entire part, that is 0.3 millimeters per side, and that is incredibly accurate. Even if this wasn't rubber mounted, there would still be roughly about 0.3 of a gap around the bolt anyway. And with that, it's time to prepare for welding.
Oh, you can't weld cast aluminium. Ooh.
Of course, cast aluminium is weldable. Look, I'll show you.
Who needs a bulb?
While I'm chamfering, Luke is getting the cardboard templates cut out, as we plan on adding the strength back into the part by bridging the gaps. I'll explain a little more later on. Right, so we've got all the patterns for the infills cut. That's going to strengthen everything up, so the next time Alex crashes the car, it won't break in that point.
If that's been engineered to be a weak point, you could kill the engine.
That could be a possibility. If you're traveling fast enough to break this engine mount and break an engine, I think it's going to be the least of your worries. You're just going to have an engine in your head. Now we start our welding procedure. Now, a welding procedure is basically the method of welding something correctly. So some nerds and scientists and stuff sit around and they weld different materials and then they break them apart and test them and strength test them and stuff. And then they come up with a weld procedure and then they put that online and then we find it. So the number that we're interested in is ALSI7 MG 0.6, but the street name for it is A357. A357 has the same silicon content, more magnesium and a little bit more beryllium compared to A356. It's about 21% stronger, nothing revolutionary, but it's much better than, say, like your average motorbike casing. A356 is what's commonly used in cast material, which is great for welding, but we've got A357, which is even better for us. So there's two different types of rods that we can use for this, is a 4047 and a 4043. A 4043 is better at gripping onto things, but the 4047 flows a bit better, and it's not as strong as a 4043, but we're putting lots of bracing in there that will account for it. I reckon we can get this whole thing about 25% stronger than Bugatti did it, in my opinion.
Oh, that will never be as strong as Bugatti made it.
Correct. Now, when this part has been made, it was sent to be tempered. That will bring it to T6 hardness state. When I weld it, it's going to reduce by 35% down to a T4 temper state. Now, we're aware of that. That's not a problem, because what we're going to do is fill in these casting voids with gussets. And what that will do is increase the strength of the area by roughly about 35%, in my opinion. A part of the welding procedure is you need to bring this up to 200 degrees. So I'm going to pop it in the oven. And when it comes out, it's going to be ready to weld. So I'm going to do all my cleaning now, because it'll be too hot to touch when it's finished. Now the part is up to temperature, we can get it mounted onto the table solid and start welding. That is welding so nice. It's just flowing really nice, very low in impurities. Fair play, Bugatti. That has gone really well, really well. Like perfect. Was not expecting it to go that good. I've got 100% confidence in this. Right, we don't want it cooling down too fast, so we're going to put a lot of gloves around it. If it cools down too fast, it could affect either the hardness of it, so we don't want it to bend, or it could crack. So we just stock up loads of gloves, and we want that to cool down over about 20 minutes instead of minutes.
Won't that twist and warp when you weld it?
So one of the reasons we put it into an oven first is to bring the temperature up. So twisting and warping usually happens when you overheat one area more than another side. So say if you had this piece of sheet here, if I warm this side, it will expand. And that's when it will start to twist and warp the panel. But if I heat the entire sheet evenly, the whole thing will expand together. So we've put it in the oven for a few hours to get it all to expand together. Then we've clamped it to this table, and then we've covered it in gloves, like you've seen earlier in the video, to keep that heat in that side of it while I weld this side. We need to add strength by welding in the plates you saw us cut earlier. This will help bring back the strength of the part. So after the last bit of welding, we let it cool down a little bit, give it a quick clean, and we are done. If anybody's wondering about the power tools I'm using, they are called flex tools. They are a personal favorite of mine, that's why I use them, and this is not an empty sponsorship. This is genuinely my choice of power tools. So if anybody wants to purchase any of these flex tools, I'll put a link down in the description. We can get them in D&M tools, and discount code below in the description. So this is done. I'm very happy with how it turned out. I've not had any complications that I was expecting. It rings. Brilliant, perfect. Everything went really, really well. The next thing we're going to do is get it bolted down to this table, and we're going to get a thing called a CMM, or a faro arm, to check all the important points. Now, the boys over in America have 3D scanned this, and from my previous experience in engineering, a 3D scan is a picture that you then draw over, and that's how you get all the important measurements. 3D scanning has come on a lot since I've 3D scanned things. They are going to be very, very accurate. However, the right way of doing things is to get a CMM or a faro arm and go around and touch all the really important points with this little sensor. And that gives an exact point in space of where all those important parts are. Now, the really, really important bits that I'm concerned about are the crank position sensors. Now, because it's a really powerful engine, and it's going to be revving quite high when it's doing 200 and whatever miles an hour, it needs to run correctly. If these holes are out by even 0.01 of a millimeter, you'll start to get misfires when the engine's revving quite high. So now we've completed the scan, we can take that information and share it with the boys in America. Again, we didn't see them using the CMM machine, but they may have, we don't know, but we need to make sure this is right, just to make sure it's super accurate and it's as good as it can be. Next, we're going to give it to Jish, our faithful cameraman that you never really get to see, and he's going to bring it over to the Aqua Blaster and get it cleaned.
So we're going to get this in the Vapor Blaster, get it all clean, ready to hand over to Matt. And there we have it, one lovely clean gearbox mount.
Mad! Oh,
Now we have a full engine mount.
that is proper. Yes.
Effort we've gone to with this is 100%. This is absolutely 100%. So see all these little cavities and stuff?
Yeah.
So like these bits? There used to be holes like this.
Yeah.
Covered all them in as well.
Yeah.
So it's stronger, it's back to...
I want to clear something up as well, yeah? So there is literally about 90 million comments in the comment section of engineers, yeah, saying this bit was meant to break. Is that right?
I have a suspicion they're correct.
Really?
So, that's why I haven't filled them up completely. So there's lots of schools of thought about this, lots of different ways of thinking about it. So the cavities are there so it cools evenly, so you can't have a thick piece,
Yeah.
because it'll cool at a different speed to the thin piece, and then it could potentially crack.
Yeah.
So they keep everything roughly about the same thickness all over.
Yeah.
Part of that, it could be they've made what they call a fuse, because that engine's mad expensive. This is pretty cheap to make.
Yeah.
They might charge you 100 grand for this if they were to sell you one. So if you crash the car, and this was solid, it might kill the engine. It might snap the engine.
Right.
In case.
Right.
So they'll let this, all the force goes through this, and this would effectively be a fuse to protect the engine.
It's crazy that the speed he was going, and it doesn't seem that bad of an accident, and this is broke, which like seems mental to me, because then they've got to split the whole entire car for this small piece. I'm like, why not just make it stronger?
It's a happy accident. I think they made it like this, and then the FEA'd it, so they basically stress tested it in CAD.
Yeah.
And then they're like, oh, it snaps across there, or they stress tested it in that position where the engine's hanging on it all the time. never put any load through that way. But when they
because I'm guessing the load going that way would be fine.
it sits like that all the time. I think it might be a happy accident, and then they probably crash tested a few of them and it snapped there. Like, oh, it saved the engine. Brilliant, cool, send it. It could have been like that. I don't think it was really planned into it, because there'd be more evidence of it being
like an obvious.
Yes.
Okay, cool. That is pretty sweet. I like it. Let's this we know is 100% going to work. Thanks, Bob.
Excuse me, is that a plastic parkside caliper? You're such a cowboy. Ooh.
have a little grow up.
Oh.